So, up to now what we have discussed is for spurious charge transfer states. Of course, there are cases where you have a real charge transfer state, a state where the charge transfer is not a spurious property, and one of the common examples is actually dyes which are used for dye sensitized solar cells. So, this kind of dyes has generally three regions. One is the donor, these two rings are donor actually, then there is a linker, and then there is a part which is actually attached to the surface. So, we are going to calculate its excited state, and for this particular excited state the first state is actually charge transfer. And now let us do the calculation. You can find out the geometry here, and you can make an input file and submit the calculation. So, I already have downloaded the geometry here, so I will open it with Avogadro. Of course, you can make and edit it and make it a manual input files also. So, I go to Orca, because I want to see it's a real charge transfer state. So, we are going to use cam bitrilip Rij cos x . So, it is MA def to SVP, that is what we are going to use our basis set for. It is a minimally augmented def to SVP, and of course, we want to see the molecular orbital. So, that is why we want to do it a large print. The molecule is slightly big. So, let me give you max score 2000 and then percentage TDTFT . I am just calculating 4 roots because I know my first root itself is a charge transfer. So, let me generate the input file. Now, if I run this input file, first of all there is a spelling error. So, let me correct it, bitrilip . Okay, this file once I run it, it will take some time to finish the calculation. So, I will use the output file which I have already run, and just to give you an idea how much time it will take. So, it takes half an hour to do this calculation. So, I have done the calculation beforehand, and if you see the excitations, the first root is from 89A to 88A to 89A. That means this is actually an HOMO to LUMO excitation. So, I will have to find out where the SCF is. Yeah. So, this is where the SCF is. So, you can just use the control F, it will come with the search option, and I have searched with final, and you can see that my HOMO is 88 and 89 is the LUMO. LUMO is negative here, do not get perturbed by this one. DFT orbital energy actually does not have so much of physical significance, especially for a chem B3 functional. So, basically my 88 to 89 is a charge transfer excited, this is what the excited state is dominated. At this point, if I do not know anything beforehand, I cannot tell that it is a charge transfer excited state or not, and that you can only tell once you open the output file with Chemcraft and see how the HOMO and LUMO looks like. Go to tools, render molecular orbital, so remember the Chemcraft start from the counting from 1, so HOMO is 89, LUMO is 90. So, this is the donor orbital list. So, you see that there is a considerable density on the to this to benzene ring. So, this is my donor orbital. My acceptor orbital, once I go, you see that the orbital density orbitals from here, the isosurface from here actually reduces, and the isosurface. So, this was the donor and this is the acceptor. So, in the donor the orbitals are there is a considerable isosurface is here. For the acceptor, the isosurface is entirely on this side. So, this side the isosurface has reduced to a large extent. So, you can consider is a charge transfer from this part to this part of the system. So, this is how a actual charge transfer state looks like, which is not a Spurier state. So, up to now, so you have seen three kinds of excited state: valence, Rydberg, and charge transfer. And up to now, what we have performed is single point calculation, where we tried to do calculated excitation energy on already optimized ground state geometry. But before going to the geometry optimization part, this is the homework problem. So, these are two isomers E and Z of these two molecules, and they are structurally slightly different. So, you are supposed to calculate the excitation energy and plot it through Chemcraft to see how they actually looks like. Remember, one is E and one is Z. You can get the geometry of these two isomers from this link, and from there you should calculate the experimentally visual spectra for this. You are supposed to use Chem B3 and calculate at least for 30 roots, and def to TZBP basis set what you are going to do the calculation for. So, this is your first homework problem for the day. For your geometry optimization, we have discussed that in some of the cases we may need to optimize the geometry of the excited state, because the geometry of the excited state can be slightly different than the ground state geometry. Many of the chemical processes actually takes place through the excited state. Some bond breaking actually happens in the excited state, certain reactions actually take place in the excited state. So, sometimes it is important to do the excitation energy. So, the way you should tell the program which route, because each excited state will have a different geometry. So, the geometry optimization needs to be done in a state specific way. So, how we will know for which excited state you need to do the geometry optimization, and that you can specify by the option I root is equal to 1. By default, it will optimize to the singlet state. If you want to optimize it to triplet state, you need to use additional keyword, which is I root multiplicity is equal to triplet. And in certain cases, what will happen is that the ordering of the excited state might change during the optimization. So, what is considered as to be the first excited state in one geometry during the optimization, what may happen, that may become second or third, fourth. So, whatever is considered to be the first excited state during the starting of the geometry optimization, what may happen is that the geometry may change to a completely different geometry when you are doing the optimization. So, when you start with a single geometry, when you start with a single geometry, the first excited state may get converted to a third or a fourth excited state. So, then question is that which geometry you are optimizing at. So, the idea is to follow a particular route, so that even the ordering of the energy ordering actually changes, you still optimize for that particular kind of excited state. Remember, the definition of ground and excited state is very clear. Whatever is the lowest energy state is the ground state, and the state which is the next lowest is the first excited state, second lowest is the second excited state, third lowest is the third excited state, like that it goes on. Now, at different geometries, the ordering of this state can be completely different. So, to make sure that it has converged to a geometry of a particular excited state, sometimes you need to use the option follow route, might set to be true when and during the optimization, and the other check is that in the beginning of the optimization and the end of the optimization, you plot the orbital and look like the orbital still looks very similar, to make sure that the follow route option has worked properly. So, let us now try to do the optimization. So, this is the optimization of formaldehyde for the first excited state. So, this is how the keyword will look like. Let me use the Rij cos x option because I want it to get it fast. And see, here I am optimizing an internal coordinate. The reason I wanted to optimize in the internal coordinate is that I wanted to maintain the symmetry of the original system, that C2V. I could have in principle optimized in Cartesian coordinate. Also, when I say Cartesian coordinate, means I give the input in Cartesian coordinate and then it is converted to an internal coordinate, but in that case symmetry of the molecule may get changed during the optimization, whereas if I am specifying the internal coordinate in a specific way, in most of the cases the symmetry will not change during the optimization process. So, let me make a folder. So, I open it in MovaXterm here. So my optimization is done. Maybe a good idea to open it, the output file first. So this was my initial values. So first it will do the SCF, then we'll do the absorption, and then we'll do the calculation. Let us go to the end, because what I want to see is now the dominant contribution is from 7 to 8. And in the beginning, also it was 7 to 8. So at least the nature of the excited state has not changed, but one need to confirm it using some kind of a, orbital analysis. So we'll do that. But before that, let us see how the geometry optimization has went. So let me open it with Chemcraft. So at the initial geometry, if you see, the bond length was 1.2518, and if you see it at the optimized geometry, the bond length has increased a slightly little bit. And the reason you can let us see the first how the orbitals looks like. So let us first make the orbital at the initial geometry. So in place of opt, I need to give large print. Its initial MO, all files, so I've saved it like a txt file. Let me make it an orca np file. So remember, the excitations was HOMO to LUMO. So if I render the orbitals, so this is n pi, and this is a pi star kind of an orbital. Both of them are actually looks like an antibonding orbital. This is a pi antibonding orbital. So, this is how the initial orbitals are. If I try to see my final orbitals, and that I can easily make by starting from the input file, XYZ file, zero to 1 H2CO dot XYZ. So, I will open it with Chemcraft. So, the nature of the excited state remains same during the optimization process. So, we have got to the proper geometry. This is actually the test. So, you need to do the generate the molecular orbital at the beginning of the optimization, at the end of the optimization, and you should find out that the nature of the state remains same during the optimization. In that case, your optimization has happened properly. If it is changing in between, then maybe you need to use the follow route option. Your second homework problem is to optimize this NN dimethyl aminobenzonitrile DMABN. So, this molecule has two fluorescence peak. The first peak happens due to an local excitation, and the origin of the second peak has some debates what is the origin. So, you are going to optimize the first excited state at CIS F2 SBP level geometry. So, this is going to be your homework, second homework problem for week 10.